Be live?
Yeah. Yes, we are live.
Be live? All right. Start then.
Yep.
All right. Hello, everyone, and welcome to today's brand new episode of Corecast. I am your host, Tim.
I'm Sahil. Welcome, everybody, to a brand new, exciting episode of Quirkcast. If you haven't already, you join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, you ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So Tim, this is effectively a continuation of last week's episode, where we were discussing essentially the overarching theme of how physics is connected to machine learning. And in the previous episode, for viewers that didn't catch it, we discussed essentially how there's quantum mechanics, thermal physics, and how thermal physics, is connected to machine learning, and how quantum mechanics is connected to thermal physics, and mostly spending the time on the connection between quantum mechanics and thermal physics. So, yeah, anything you want to add about that, Tim, before we jump into this episode?
Yeah, not too much. Yeah, basically, the basic idea is that quantum physics, there's quantum noise, and thermal physics, there's thermal noise, and machine learning also has, I guess, data noise. And the way all three disciplines sort of treat noise, there are similarities, and turns out that these are not just superficial similarities, they're actually perhaps a deeper connection, and which we'll go over today.
Yeah, I'm excited. As many of our audience members are. So let's start and talk about maybe now we're connecting thermal physics to machine learning. And so wanted to start with one of the basic concepts in thermal physics, which is Brownian motion. So maybe, Tim, could you give an overview, really basic instance of how can I conceptualize what Brownian motion is and what's the big deal? Like, why is this even important?
Yeah, I would say, one of the basic ideas of physics is this concept of reductionism. For example, if we look at gas, like air that we're breathing, or water in a pond, the way physics study the subject is to break it down. Basically, well, what is water made of? You can look inside and see that they're made of water molecules. And if you look at air, gas, in order to study the behavior of gas, we zoom in and we see, hey, look, gas is made up of gas molecules, right? And why do we care about Brownian motion? Back in the days, Brownian motion was, back in the days, people didn't know that you could break things down like that. That water is actually made up of smaller molecules. And one of the proof that people had was the theory of Brownian motion. It says that, hey, look, if water molecules are ultimately made up of individual molecules that are jiggling super fast, we should have some ways to see that experimentally. So lo and behold, scientists, physicists back in the days, for example, you can put a little sphere that's large enough that you can see in a microscope. You can put it in water, and because of the molecular nature of water, it will jiggle, even if you don't do anything to it. It will jiggle a little bit and trace out a path called the Brownian motion. Allegedly, I think Einstein worked on that problem, and the Nobel Prize was awarded in 1926, not to Einstein, but to an experimentalist. So some would argue that Einstein could have had two Nobel Prize, but not on his relativity. But then, stories aside, this is where it comes to be. Brownian motion was kind of the anchoring point for proving the molecular theory of these objects. And as we will see, this idea of breaking things down to the individual tiniest constituents actually applies in perhaps machine learning as well.
Yeah, I want to touch upon, I want to get a little bit more intuition on Brownian motion. So could we say it's like the continuous analog of the random walk? where, random walk takes discrete steps where, like, let's say I'm, a drunk person and I live on this, like, I want to go, I can either move forward or backwards and I flip a coin. If it's heads, I go forward by one step. And if it's tails, I go backward by one step. And random walk is sort of the study of how this process evolves of, like, what is the chances of me reaching home? Imagine if we're like three steps forward, different ways of getting to three steps forward, which can be like, two steps forward, four steps back, and like five, or I'm kind of losing six steps forward, or five steps forward, something like that. Um, yeah, and so could we view Brownian motion as the continuous analog where I take like infinitesimal steps instead?
Yeah, I mean, I think you can say mathematically it's designed this way, but I would say in nature, of course, there is no, like, in nature, ultimately, all these processes are discrete. For example, like, why are gas jiggling around? Because they bump into each other and they move. And random walk was the mathematical framework to study these processes. It says, hey, if every second you have some random chance of going left, right, up, down, front, back, and if you zoom in and you see that, hey, you know what, each second is actually made up of microseconds, let's say, and each microsecond you take a forever smaller step. And Brownian motion is the limit at which you just look at smaller and smaller interval and see this noise repeats. And it turns out that this mathematical idealization was actually useful mathematically for us to do calculation. And in most cases, this approximation is very, very, very good, because look, if for air molecules, there are trillions and trillions of air molecules, right? And of every second, you got probably bazillion of them hitting any single object. So it might as well be continuous. So Brownian motion is sort of, and I wouldn't emphasize so much on Brownian motion itself. Probably there are many other different buzzwords that are on similar topics, like maybe Markov chain models. A little different, but ultimately very similar. It's just the idea that there is noise in the system. It's like imagine you're trying to study how a car moves, but the car doesn't just move straight. It's got noise built in. This I would say is the essence of Brownian motion. Movement, but with noise everywhere.
Gotcha. That makes sense. So we were talking about a reductionist type of approach that you mentioned early on during when Brownian around the time when Brownian motion was discovered, or rather gases were modeled that way. People didn't know that, oh, like, water was made up of smaller things. So we can touch upon that like you have this gas and it's made up of these individual molecules that are all bumping to each other, and each individual molecule follows what we just describe as Brownian motion. So, obviously I can't track, like, individual molecules precisely. There's too much stuff happening around, which is probably why you choose Brownian motion. And that may ultimately describe something greater, like maybe certain macroscopic properties of the gas. So can you explain that more, like delve into that a bit?
Yeah, and this idea in physics is generic. Like back in the days, let's say when people didn't have the theory of molecular physics, then certain phenomena were very mysterious. Like how come water will freeze? And it turns out that if you don't realize that water is a molecule that are most of the time they're bumping around each other, but they have some attractive forces, you really can't, like, how are you gonna realize why water freezes? And there's no other way around it. So the theme of physics has always been that, it's not that we truly care about the individual molecular dynamics, although sometimes we do. Of course, when you run experiments, we do want to know the truth. What is water made of? But the real goal is, first we break down the problem into its smallest bit. Then once we have the foundations right, we build it back up using rigorous mathematics and to see what we call emergent phenomenon. I know this is like a buzzword, but in physics, it is meaningful. You add up all the little constituents. Their laws might be simple, but when you sum them all up, you look at the system as a whole, you take a bird's eye view, interesting phenomenon emerges. Like, for example, water can freeze. and they can freeze into snow or snowflakes. Like a snowflake is very intricate. You wouldn't have guessed that from just a puddle of water, right? But if you go through this reductionistic step and build back the theory up, you will actually find out that, hey, look, water can mix snowflakes.
Huh. Very, very interesting. I guess okay, so what you're saying is that like this gives rise to the notion of emergence where you have these particles that follow Brownian motion, which is this jiggling around, random jiggling, and they give rise to these macroscopic properties of whatever you're observing. So maybe like the temperature of the gas in the box, for instance, or maybe like the average speed of particles moving around. And um I guess like can we, in keeping with the theme of this episode, can we give an example of like how you can take concepts, not necessarily Brownian motion itself, but concepts related to what you just talked about with Brownian motion and how that translates to like some other field that people didn't expect, such a thing. Like, yeah.
Yeah, I mean, I mean, like in physics, the application is of course enormous, right? From the gas, you go to the individual molecular behaviors, and then as you zoom back out, you realize that they can form solids and liquids and all kinds of interesting phenomenon. Um, and you can probably maybe the most well-known application of Brownian motion, or at least analogs of it, will be the stock market, and that's like we mentioned in previous episode. This is one of the reasons why Wall Street loves the higher physicists, because it uses very similar math. So you can think of, if you look at the stock, why does the stock price go up or down? It's because individual people or institutions are buying shares and selling shares, and you can thought of those are noise, right? Like someone wants to buy one share at this price. It's a little interaction, but when you add up all that, you realize that, hey, stock can go up or down. And then ultimately, when you zoom out far enough, stock might even crash or go parabolic, right? And these behaviors, of course, it's not just Brownian motion, but it definitely depends on some aspects of Brownian motion. And this is probably one aspect. I think the other I mean, I'm sure you can apply to many different fields, like maybe probably in the realms of biophysics, like look at evolution, for example. Like some creatures might live or die. You can think of it as a tiny little sort of chance, right? But then overall, eventually species can evolve to different kinds of interesting configurations. So things like that. But most of these applications are very science-esque, I would say.
Yeah, I mean, I'd conjecture and also say maybe things in neuroscience might apply this. I mean, there's the thing like you can model the brain as a bunch of neurons all interacting with each other, and maybe they obey simple rules, but the rules give rise to these really intricate emergent patterns, such as us, for instance. So I don't know, just a thing I've seen occasionally here and there.
Yeah, I would say certainly part of that is buzz. You can argue,
Hmm.
is it just a hammer looking for a nail? Um, but I would say the emphasis is on noise, right? Like there are situations where the noise doesn't matter, right? Like who cares? Who cares where this random walk behavior? When that's the case, yeah, then it doesn't matter. But in many situations in the world, the noise is important. Of course, in stock market, the noise is everything, right? Like it causes things to crash or go. It causes bubbles to form, like stock market bubbles, not like physics bubbles. And in physics, it's also important. Like without noise, or at least thermal noise in that sense, there's no reason for the jiggling of the gas is caused by noise. If without noise, then you'll be at zero temperature, and then everything will just freeze, right? Like noise is fundamental. Of course, noise a lot of times is also a proxy for our ignorance. Like noise is not truly noise a lot of times. In physics, noise is a proxy for things that are unknown, chaotic, and things that are hard to keep track. And in some sense, it's the same thing in stock market. Noise is people buying and selling stock, and we don't exactly know how people are willing to buy stock at what prices. So it organizes our ignorance. And I would say, in that sense, whenever a subject has a lot of noise or has a lot of ignorance involved, then these sort of theories in physics becomes very important.
Hmm. I see. I see. So ultimately the connection we're making here, just to kind of zoom out and look at like why we even brought up Brownian motion, is like there are a lot of other systems, not necessarily just only in physics, mentioned stock market and a bunch of other fields, where you have individual like entities, for lack of better words, that may obey simple rules, but the system as a whole exhibits this interesting emergent phenomenon when you sum up in quotes the interactions of all the different agents in that system. Is that fair to say?
Yeah, I think that's fair to say. Clearly, a lot of this system, there's a gap. Like if you break
Yeah.
down the system into its individual parts, it looks very
Mm.
simple or deceptively simple. Like the stock market, just people buying or selling stock.
Yeah.
Why would it crash or there'll be bubbles, right? Like,
Mm.
you wouldn't know that in advance. Just like how you wouldn't know that water can make snowflakes. And the same thing, maybe apply to like machine learning or AI.
Yeah, and one last example I just thought of as we were talking about this is traffic is a great example. The goal is not to hit the other cars, and so when you encounter traffic, that's just like everybody following the same rule, which actually segues nicely into the next thing I wanted to talk about, which is phase transitions. So in the context of traffic, you could have like cars moving smoothly, and let's say some disturbance happens, an accident happens, everybody stops, and it just kind of propagates through the whole road, and now you get everybody in gridlock, and like the environment's completely changed in terms of how people are moving. So maybe Tim, it'd be nice to give what like phase transitions mean in physics, and then we can give other examples of like what how's that relevant to the greater discussion.
Right, right. Yeah. So one of the interesting things about this reductionist approach and then kind of building up the system is that when you study macroscopic quantities, sometimes what you find is there are different regimes with very, very distinctive behavior. And the interface between them is very, very sharp. And a common example of course, in physics is the different phases of water, for example. It's the same water molecule, right? And if you make it cold enough, it forms ice, right? And if it's warm enough, it becomes the water. And if it's even hotter, then it turns into liquid. Like that's these are drastically different behaviors, right? And it's such a behavior is not obvious if you zoom into the molecular level, but if you zoom out, these can be explained by emergent properties that are fighting each other. For example, you can look at the overall attractive forces and the repulsive forces to see how they fight against one another. And at some threshold, if some of them wins, water will freeze. There's more attractive forces than not. And then there's also like a cumulative effect. When one water molecule attracting other, the other water molecule might align because water is polar. So the shape will change and it amplifies. It kind of has this self-amplification effect, so it can attract other water molecules to come join them. So that's why in physics we see this sharp behavior, this self-reinforcing behavior, where a small effect can get amplified, but it depends on the overall behavior of the system. When the temperature is too high, there's too much noise, and once again, noise comes in. It's important when the noise is so large. the water molecules is not able to settle down. So you have this interesting divide between water and ice where there's a sharp contrast. Now, if you bring it to other system, it's because water is relatively well understood, yeah. But the question is, there are other systems in the world that are not water, but yet they exhibit behaviors that are very sharp, very sudden, very unexpected. And the idea is maybe something like, water freezing or melting is responsible for these effects.
So are you saying like, let's say I gave you I'm thinking how to describe this. Eh, Like, contrasting this from our like the topic we were just talking about, which is Brownian motion, you can't really like predict how phase transitions will happen given the simple rules of like the system itself, or what I'm just trying to understand like what is sort of the distinction in terms of how we're going along this discussion.
Yeah, basically you have to zoom out. You have to add. You have to combine the effects of all the little bits and pieces of your system together. And when you zoom out, you see a bigger picture. Like for example,
Mhm.
the little bits maybe even though they may cooperate in
Yeah.
certain circumstances, and then when they do that, certain emergent phenomenon happens. Like it's like the
Mhm.
stock market, right? Like maybe one person buy the stock. Normally it's random, but maybe just by chance, 10 people want to buy the stock at this price, and this price goes up. And then someone's like, "Hey, look, man, the price is going up. Let me buy it too. I want the price to go up even further." Then more and more people pile in, and then you get this like emergent behavior where hey, like people just like buying the stock all of a sudden, right? For no reason, right? There's sort of this self-reinforcing behavior, but you have to zoom out in order for you to see that. And of course, maybe if you're smart enough, you could predict some kind of that behavior. But usually in physics, there is a systematic way of you to zoom out, to see the bigger picture, to see the sum of its parts, what the effects are.
Hmm. And I want to touch upon your terminology of zooming out, because when I think of zooming out, it like I think if I'm looking very closely at some piece of material and maybe I see like, the atoms or, things that are akin to atoms, and I zoom out and then I see like the piece of metal or piece of material and I zoom out further and I just see more of it. Is it a spatial zooming out, or is it zooming out in a more abstract sense?
It could be either way. Like in condensed matter physics, there is literally a sense of zooming out. Instead of looking at one atom, maybe you look at 5 atoms to see their collective behavior. Maybe, and then you zoom out, you look at 10 atoms. This is the theory of renormalization, and it was actually awarded a Nobel Prize for a study like that applies to phase transition and whatnot. So I don't want to go into details, but physicists have developed this very sophisticated tool specifically for studying how a system changes when you zoom out. And it has been successfully used to study systems like water, how they freeze, or like I don't know anything about quantitative finance, but I suspect that maybe some of that has been ported to study stock market, but don't quote me on that.
Yeah, from what I know about quantitative finance, usually the models have trouble when like you enter the regime that everyone just sells whatever they have and during crashes. But that's a whole separate topic. I guess, yeah, on that note, if I try relating it back to the Brownian motion picture, not necessarily about Brownian motion, but let's say I have agents in a system and they have some simple behavior, and in normal circumstances, for some definition of normal, they behave in a particular way, and you get these, like dynamics of the system that are, within what you can predict. And then some disturbance or something happens, and essentially the dynamics completely shift. So could I view that as like changing of how like is it an incomplete understanding of like the simple rules of the agents, or is it something even broader than that, or something like deeper than that?
No, I think it is deeper. Like even
Okay.
though, I mean, even though a lot of times noise comes from ignorance, right?
Hmm.
But the behavior we derive is genuine. Like
Hmm.
it's telling you that like the reason it works is because the system doesn't care about the details of its bits, and that's generally true. You know, like sure, let's say you can completely solve the equation of every individual molecules, and you do
Hmm.
that. Let's say you're a super powerful computer, you do that, yeah.
Hmm.
Versus if I just ignore that and say, hey, it's just noise, it's random, you more or
Hmm.
less get the same answer. And
Hmm.
this is the behavior of universality, and
Hmm.
it tells you that even though you make these approximations, even though maybe it's not 100% realistic, but the result that you get generally is applicable because like there's a general theme that large systems, they don't exactly care too much about the details of the exact details of the system. Maybe it matters a little bit, but like the general behavior will you get it.
Hmm. I'm curious also, like, this may be a slightly tangential question, but more for my curiosity. When we, I guess, like, the concept of emergence, when you say like, oh, the whole is greater than the sum of its parts, is there like a, I guess, a physics intuitive understanding of where that comes from, that you have these agents that obey these simple rules, and then like together they like do this incredibly like complicated thing that you really wouldn't have been able to like tell just by looking at the individual agents themselves?
Yeah, I mean, it really comes down to whether certain effects can accumulate, basically. You know, and the stock market is a great example, or the traffic jam,
Okay.
right? If one car stops, the car behind it has to stop. And these
Yes.
rules initially, you can't tell whether they reinforce one another or not if you just look at one of them. But in physics,
Mm,
there's so many instances where even the tiniest effects, when it gets reinforced over and over and over again, can lead to huge behavioral changes. And another example is like superconductor, right?
mm,
Electrons, normally you think electrons, they have the same charge, they repel each other. But in a
yeah.
metal, electrons, their behaviors change. And I don't want to get into details, these electrons turn to what we call quasi particles, and the properties changes a little bit. It turns out
Mm,
that when you cool down to very, very low temperature, there's just like a tiny, teeny bit of attractive forces between them.
huh.
And it has due to the structure of the lattice, whatever. And this attractive forces can accumulate, and ultimately electrons and two electrons can form a bound state called Cooper pair. And that's the basis of type 1 superconductor. When they combine together, they can flow without resistance. I don't want to get into details yet, but it's just that this tiny, tiny little bit of attractive forces, you wouldn't expect it to matter in any way, but it's because
Mm,
it adds, right? All the other stuff, the noise, may be canceled. But this, initially, what looks like noise
mm,
can get bigger and bigger and bigger. Um, and
mm.
then it turned into something very dramatic. And I think these analogies are actually very much audible in the AI language.
Yeah, yeah. It's that's actually really interesting that feedback loops play a central role with this. Yeah, there's an audience question that came in. It could be directed towards me since I use this term, but maybe we can both take a crack at it. Which is, what do you mean by the whole is greater than the sum of its parts? Don't you mean the whole is equal to the sum of its parts? I'll just take a stab at this, and then Tim, maybe you can jump in. What I mean by whole is greater than the sum of its parts is that you get behavior that's like more complex than what you see with the individual agents. So for instance, if I look at like the neurons in my brain, each neuron has like, I mean, it's still not as well understood, but let's just say for argument's sake, each neuron takes in electrical signals and then passes, sends also electric signals out, and yet I get this like emergence of consciousness and intelligence and many other things as well, and perception and whatnot. And so that's kind of what I'm referring to as like the whole is greater than the sum of its parts. I don't know if you wanted to add anything to that, Tim, or yeah.
Yeah, I think it's just a simple phrase that says what you get is more than what you expect. I think like a
Mhm.
good analogy would be like stock. Like imagine one person buys stock goes up by $1, let's say. Okay. Well, maybe I would expect that if 100 person buy the same stock, maybe stock will go up by $100. That's reasonable, right? But maybe that's not true. Someone buys a stock, goes up by $1, and that person is like, oh man, stock is really going up. Maybe when 10 people buy the stock, it goes up by $1,000 instead. And this is what you mean, like this sort of this self-reinforcing behavior, or self-defeating in some cases, that it when you just add them up, you don't you, that's not the answer you get, right? It's just sort of this general theme, like you can't just sum them up naively and get the right answer.
Yeah, actually, I'm glad you gave that answer, Tim. It actually leads into the next thing that what we want to talk about. So, what I would say to the audience member in terms of what we're about to talk about is that when you add these two things together, they just don't add linearly, but add in greater than linear, as Tim was saying. So this ties into scaling laws, which is what I wanted to talk about next. So, Tim, can you explain what scaling laws are? I mean, we see them in the context of many different things from physics and nowadays to neural nets and machine learning. But before we dig into what those specifically are, can you just explain like what is a scaling law?
Yeah, I think scaling law is a general thing. It tells you that some properties, like for example, there's like a paper, almost like a well. Anyway, maybe not talk about that. Like in statistics, a lot of times you look at certain distributions, right? Maybe you can look at the amount of the number of people with certain income, or like the number of words per document. Like in Shakespeare, how many words appear how many times, right? A lot of times you see this behavior where the maybe the most frequent word is very high, and it kind of the graph kind of peters out, and you can look at, well, what is the shape of that graph, right? And it turns out that the shape of the graph a lot of times looks like what we call a power law, like maybe like 1/x². Maybe the second most frequent word appears I don't know, maybe that's not the best example, but you know what I mean. It's some law that goes uh
Yeah, I mean, you could also talk about the Pareto principle, that like the 80/20 rule. I'm sure people might have heard of
yeah,
that.
it's the idea that these distributions tend to have a large tail, but I sort of don't want to emphasize that. Like
Yeah.
why are these power laws anything? It's just some mathematical function. Why do we care, right? In
Mhm.
physics, power laws are some things that we call power laws are distribution shapes that are kind of shapeless because it's so simple, right? Like it's 1 over something to the power. You imagine a complicated physics equation, maybe like 1 plus. Normally a physics equation should yield something more sophisticated, right? Like maybe 1 plus x squared plus x times y divided by 2x, something like that, something more complicated. How the heck does it produce something so simple? And in fact, we do see that actually for systems that are in phase transition, right when they are right at the phase transition.
Hmm.
For example, when water, maybe that's not strictly correct, but anyway, let's go with that. But let's say when water, it's right about to freeze or melt at that moment. And the general law is that in that moment, the system kind of can't seem to decide, right? And so in some sense, all the laws of physics kind of goes out the window. Like all the parameters, like the distance between molecules goes out the window. And the only thing left is just the intrinsic property of that phase transition. And the belief is that when this happens, some of the laws actually get simplified because the system cannot decide. It's fine-tuned. It's very fine-tuned that all the complicated stuff gets canceled out. And then you're left with very simple distribution. why it matters is that when people look at distributions in the real world, like the amount of ice cream that's sold in a given year, whatever, like, some people use that as an argument for like, hey, maybe there's some critical behavior like phase transition happening here. Um, Although generally that's not true. There was like a mock paper that says, hey, we find power laws everywhere. Um, but but it is true that for a system at a critical point that can't decide whether it wants to be water or ice, we generally see some sort of power laws emerging. And that's why when people see power law, they're like, ding, 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 huh, interesting.
Yeah. I'll add to this and give a few examples from what I've seen to, complement the discussion. One example I've seen in like medical cases, like given the mass of like an animal or whatnot, how do you decide how much more of the drug you want to give? So let's say you give a mouse X amount of some drug and you want to decide, oh, like a human, has X times more mass. Like, do I want to give, let's say like I'm just going to give a number, say 10,000 times the mass or 100, or let's say 1,000, for example, 1,000 times the mass. Do I want to give 1,000 times more of the drug? Do I want to give 100, like less than 1,000, or do I want to give like 1,000,000 times more of the drug, for instance? So that's an example of what you can ask. There's also questions of like, why can an ant lift like 1,000 times its body weight, but when you scale up to humans, we only can lift 2 or 3 times our body weight? So those are examples where scaling laws come in, and hence the name scaling. Like, what happens to the behavior of a system as you scale it up in size? And there's a really great book by this physicist named Jeffrey West, or Weist. I don't know how to pronounce his last name. And he talks all about scaling laws and complexity and how they appear in different domains, ranging from medicine, as I was talking about, to like cities. How does economic productivity scale as you scale the size of a city? Companies with scaling with number of employees in terms of how much revenue do they get, and things like that. And so, yeah, so those are essentially where I've seen that. Yeah, uh, yeah. So I guess Tim, can we touch upon like where scaling laws come into neural nets and machine learning? Like, why are those relevant, especially with the LLM tools such as
Yeah.
ChatGPT, Claude, and et cetera, et cetera.
Yeah, but I think first we need to at least tell the audience like what is the link between LLM and this emergent
Oh yeah,
phenomenon idea, right?
yeah,
So
go for it.
so if it's not all obvious already, basically large AI models, a lot of them are based out of neural networks. You know, for example, like I think ChatGPT, how many billion parameters they are? Like 100 billion. I don't remember, right?
Maybe even a trillion now.
Yeah,
It's
who
gone.
knows?
Yeah.
Right. But you can argue that the individual pieces of the neural networks is very simple, right? It's just numbers. You multiply numbers, you add the numbers, maybe you look at the exponential of it. And these individual neuron in a neural network, you can, when you talk to a physicist, um, they kind of act as a small component, like a gas molecule in a gas, you know, or like a seller or buyer in a stock market. These are the individual bits of the constituents of the network. And the idea is that when you train a neural network, you have bazillion of these, billions of these little neurons. They might interact with one another. And you need noise to train a neural network. You need to feed in data. And effectively, these little neurons are kind of undergoing a little bit of a Brownian motion. They're kind of randomly moving around when they're moving around. And eventually, at some point, training happens. And then you can say that there's some, the model, some more intricate structure emerges, and ChatGPT is able to generate poems and sentences and calculate, solve basic equations, right? The thought is that maybe there's some analogy between this and like water freezing or something. Let me just say that this is very like emergent fields of study, and there's some papers coming out, but nothing concrete yet. And there's also another piece of the puzzle that's interesting is what we call the scaling law, right? So people have studied large language models, and they look at the performance of your model versus the size of the model.
Hmm.
And they find that, it follows a power law. And then there also some other intricate piece of the puzzle, like large language models didn't used to be so hyped up back in the days, like a few years back. And one of the reasons was because large language models just didn't have that performance. And people noticed that at some point, when you train the model to be large enough, all of a sudden it's able to generate texts that are much better than before. And then, and that's why the hype of ChatGPT came to be. And it's even able to solve some basic arithmetic, right? So there's this sharp divide when the size of the model that gets large enough, all of a sudden it's able to perform certain functions. And on top of that, you look at the performance, it follows sort of this power law curve. And then if you like this analogy between the physics of an emergent phenomenon and large language model, and it kind of rings a bell now, then you might just scratch your head and be like, is this telling us something? Is the power law like the power laws that we see in water? And is the fact that ChatGPT able to all of a sudden do fantastical things when you make the model large enough, is that some kind of phase transition? So these, we don't have answers for these yet, but these are kind of the hints of what's coming, I think.
Yeah, it's quite intriguing that like when you scale these models above a certain size, then this emergent like behavior comes up where it's able to, as you're saying, write all these poems and stuff. If you look at like the jump from OpenAI's models from GPT-2 to GPT-3, it's pretty significant. And then GPT-4, I mean, it's a little bit less, but still a significant jump. And now it's coming into question of how big of a jump can the next one achieve. I would also say from speaking from a pragmatic point of view of scaling laws, I've heard these companies use scaling laws to essentially like say, okay, how much do we need to scale up our models by to achieve a certain desired level of performance? And that's using historical like past data of model size versus model performance, and then you plot it on this log plot, and you essentially will say, okay, by 10x my model size, how much would I expect to get in performance? How much more performance can I eke out with this extra compute? And so that essentially gives some level of guidance for
Yeah,
that.
yeah. Yeah, I mean,
Yeah.
practically that's used for that. But you can argue from a theoretical point of view, like, why should a power law work? Like, why should it work? And there is no reason in some sense. If you just look at large language model by itself, there's no reason why it works. Like, who knows? Maybe the law will plateau out at any moment. But so far, the trend has sort of hold pretty well. And if you buy this emergent phenomenon idea, physics may have an explanation. Of course, I'm not saying that this is a good explanation, because no one has written a paper and says, hey, large language model is a system like water freezing. No one has done that yet. I think this is still an active research field. But imagine someone was able to do that, then maybe they can explain this scaling law, because for emergent system, there's this universality behavior where the system doesn't really care about the details very much anymore, and that's why this pattern should hold, because when you zoom out, the model kind of the system kind of converges to some kind of I guess we talk about this a lot in previous episode. It's like the analogy is like water and alcohol, or oil. Water freezes, alcohol also freezes. I guess oil kind of freezes. Maybe it's not exactly the same, like
I'm gonna
wax
take
or
your
whatever.
word. I honestly
Let's just
don't
say
know.
it does, right? Like, there's no reason for them that they're totally different molecules. Like, how the heck does alcohol freeze the same way water freeze? I mean, there's some minute differences, right? But the fact that they both freeze, they can also be vapor, they can also be liquid. That's like a common denominator, and you can't explain that other than using this universality idea. It's just that when you zoom out, these systems tend to exhibit very similar behavior, and that's why. And also one thing I forgot to mention, like these scaling law doesn't apply just to ChatGPT. It like you look at the other models, they pretty much line up very well because they use the same architecture. So you can argue that, hey, look, maybe like it's kind of like water freezing or alcohol freezing. It's the same. Models are different, but ultimately they're kind of the same. So they follow this behavior.
Yeah, that makes a lot of sense. Yeah, so as we're coming towards the end of the episode, I want to touch upon maybe the last topic, which is I guess like kind of we discussed Brownian motion, phase transitions, and scaling laws. I'm wondering like are there other tools from physics that are used in studying neural nets, for instance, or maybe other fields, other areas of machine learning from what you've seen?
Yeah, I mean, personally, I don't know because I'm not a researcher, but I'm coming from a physics point of view, and I do see a lot of similarities. And I think the latest push is definitely on um, understand. Maybe we can understand these behaviors as some sort of phase transitions, and then we can
Mm,
justify scaling laws and maybe find other scaling laws. Because if indeed it is like a phase transition, like in physics, there should be other scaling laws, right? So that's one
mm,
thing. And perhaps we can use the theory of renormalization that we mentioned earlier. It's a buzzword, but it just means that physicists has a tool for understanding how systems change as you zoom out. And maybe
mm,
there's a sense in which you can zoom out of your model from, and by zooming out here, it's a lot more abstract now. It's sort of like I have a neuron, and in my neural network, it does multiplication and addition. But maybe if I zoom out, maybe multiple neurons can sort of behave like a super neuron. Then I can see that behavior, and that might bring us understanding to be like, well, how exactly is this neural network able to generate text, right? Like, what is it
mm,
doing? Um, and work on that front. There actually has been very concrete results, right? For example, if you train an image model, you have layers and layers of the neural network. Generally, the different layers is kind of like zooming out. Like if you look at, let's say, an AI model that tells you whether a picture is a dog versus a cat, you know, initially the model looks at one pixel at a time, and as it
mm,
goes through the layers, it might look at things like, is that a whisker? Is that a tail? Is that a paw? Is that an ear? Right? Or
mm.
or 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 maybe is it on a leash? Things like that. And you can, in some limited cases, it is literally you're literally doing renormalization on the neural network. And as you train, like the model is learning, I don't know, different parts of this feature, and then you can kind of understand why a picture is classified as a dog versus cat. So it has been fruitful, but in terms of language model, it's probably a lot harder, right? Like going on. So I think this zooming out idea is, in my opinion, probably will be the next frontier, but I don't know because this is still very new.
That's fair. That's fair. You mentioned things like as you zoom out, it gets more abstract. Could I think of that like in everyday senses, like I have neurons in my brain, they obey the laws of physics, yet like when you gather enough of them and gather different like configurations of people, then language comes about, and language itself is like very abstract.
Yeah, I mean, you could think of it this way. Like,
Hmm.
I think one perspective, to play devil's advocate, you can think of this as like, oh, you know what? This is just physicists with a hammer looking for a nail. You can certainly think that. But hey, look, if you look at the goal of machine learning and the goal of physics, in some sense they are the same. Like machine
Hmm.
learning models, like if you try, let's say you're trying to classify images, whether it's a dog or cat or a raccoon, let's say, right? you are trying to approximate certain features of the real world based on some other features that you don't have much control of, because you can't control whether the picture was taken at night or at daytime, whether it
Mm,
was taken in US or in China. So you
mm,
quantify those ignorances into noise and you do
mm,
machine learning.
mm.
And like physics shares the same goal. Maybe it's a little less abstract, but like, ultimately I believe you can use physics to describe, what's a dog, what's a cat. I guess people don't do that. But but you look at the basic features of our world and you use physics to understand what's going on. And in the same way, for things that are too hard to keep track of, that's noise, and you can quantify it appropriately. So in a sense, machine learning and physics, they are both trying to do that same thing. So I would say that link is sort of built in, like it's there.
Mm.
As long as they're both studying the real world.
Fair enough. Okay, so I have another question. This is an audience question, but not asked anywhere on the chat. This was audience member. I promised that I would ask this during
Mm.
our episode. We talked about this at length in a previous episode about the Nobel Prize in Physics. And so now looking at it from the viewpoint of this episode, do you think that like it's warranted to give the Nobel Prize in AI for this year, given that there's this connection that we're talking about?
I mean that's I would say professionally I don't have much of an opinion, but personally the answer is no. And it's mostly just because we have already hyped up AI enough. I don't think they need a physics Nobel Prize. I think they are much more deserving candidates. That I can name a dozen in my head. I also think that there's a problem with the Nobel Committee that they only awards the prize to something like once, but they don't look at improvements of it. And it's kind of frustrating, right? Like it's sort of like, oh, you would give the Nobel Prize to the first person who come up with this really basic model
Mm,
that describes some aspects of physics, but someone
yeah,
came along and really improved it, and like it really described the real world much better. But then they're not gonna get a Nobel Prize because it's not like flashy and new. And this is sort
yeah,
of similar here. It's like, oh, we're gonna just award the Nobel Prize to these foundation physics-esque AI models, but they're not really that much used in the real world anymore. But because with the Nobel Prize, we only award it to the first prototype. That
yeah.
seems a little silly to me. But that's just personal opinion.
Fair enough, fair enough. Yeah. So yeah, I think we're almost at time. And so in our tradition, wanted to give you a chance to, leave the audience with any words of wisdom that this link between physics and AI has taught you.
Yeah, I mean, of course, personally, I'm very interested in this front. Although I'm not a researcher anymore, but I still think about it. But I want to leave the audience something to ponder about. In light of these advances in AI, I mean, you can't help but wonder, what if our laws of physics is kind of like an AI model? Like, what if we are just fitting some mathematics to describe the world?
Hmm.
Um, and and it maybe there's some truth in that. Like, is nature really the equations that we write down, or are we just finding the best approximation to them using our human brain? And in that sense, it is an AI model. It's just an AI from, I guess it's not, it's artificial in that it comes from humans, right? It's an AI model trained by physicists. Let's put it that way. Uh,
Mhm.
but of course, even if that were true, there's nothing we can do about it. We're humans. We're only human, right? We can't do better. But it always makes me wonder, if they are aliens, would they have written the same physical laws? Are their laws gonna be better? And maybe to them, we have some really rudimentary, like approximate laws that are kind of just like a dumb, ChatGPT model, right? Uh,
Yeah.
it keeps me up at night sometimes, but maybe not fully because nothing I can do about it. So
Yeah. Well, yeah, that's definitely a lot to chew on. So, on that note, I want to thank everyone for joining us, and we'll see you all next week.
yeah.